All right, let's talk about 4.2, the unit circle. This is, without question, the single most important thing that you do in any trig class across the country. Let's give a definition, and then we're going to fill this thing out. And I want to go ahead and warn you that this looks very intimidating, but we'll find very quickly that there's a lot of patterns to help us figure out, and that this is an incredibly visual subject. So, here's the first definition. A unit circle has a center at 0, 0, and radius r equals 1. r equals 1 unit. In a unit circle, the length of the intercepted arc is equal to the radian measure of the central angle t. Let xy be the endpoint on the unit circle of an arc of length s. The xy coordinates of this point can be described as functions of the angle. So, that's a lot of words. And in fact, everything that we're going to talk about for the rest of this section, and honestly the rest of this class, is this definition. Everything is based on this definition. So if this definition looks complicated to you, that's okay. The rest of trigonometry is dedicated to explaining what it is. But the first thing that we're going to do is fill out a unit circle. And there's a couple of things you need to know about the unit circle. First off, it measures 1 unit. Second, it's a circle. That's why it's called the unit circle. It has its center at the origin. And we call it central angle for this one t. We also sometimes use theta instead. So it just depends on what application we're doing. You see t a lot more in engineering and theta a lot more in just math. Again, this is theta, which is the Greek letter, their version of t. It's a circle O with a dash through it. So I want to start by doing the first quadrant of the unit circle. So what we have here is the top half of the unit circle. We'll do the bottom half in just a moment, and I'll show you everything that there is to know about this. But one of the very first things that I want to do is come up here and place a quick little Cartesian system here. And I want us to recall something about how coordinates work. So if you're going to put a coordinate into this thing, and you're going to get into quadrant 1 here, this being quadrant 1, this being quadrant 2, this being quadrant 3, and this being quadrant 4. If you're going to go into quadrant 1 here, you have to go positive, positive to get there. So this is positive, positive. Remember the signs on this. This is going to help a lot. To get into quadrant 2, you have to go negative, then positive to get up there. So it's negative, positive is the sign on that. Similarly, the sign on this is negative, negative. And the sign on this is positive, negative, and that's all 4 of the possible permutations there. So keep that in mind, and we're going to use that. And what we're going to do is we're going to take these key angle measurements here. So we've got 0 degrees here as well, and all the way over here is halfway around a circle is 180 degrees. And we've got, of course, 90 degrees right there as well. And those are some of the main angles that make up your right angle and your double right angle that gets you all the way across, halfway across the circle. And what those boxes are for is we're going to convert all of those to radians, and we're going to fill that in. And then up at each one of these points, we're going to put the actual coordinate. And the unit circle is just this thing, except everything is filled out. And you'll see that this is enormously useful for the rest of the class, and is something that I fully expect you to memorize at some point during this class. It will absolutely be on a test. If that feels like a lot, I assure you that memorizing this now and having this in your head just for the class is going to help you in this class, it'll help you in calculus, it'll help you in Cal 2, it'll help you as you go forward throughout your math career. Anything that has anything to do with trigonometry, you'll have this in your head ready to go. So we're only going to do this for a few of them here, but I want to go ahead and get the radian measures, and we'll start in standard position here on the x-axis, and we'll note that this, of course, is just 0 radians, and I'll on purpose leave a little bit of room to the right here, because we're going to come all the way back around and see something in just a second. And then let's go ahead and do 30, 45, 60, and 90. And let's just take a little bit of time and practice up here converting those to radians. So we're going to do 30 degrees, and we're going to have to multiply it by the ratio. And the ratio is always pi radians to 180 degrees, and I put the degrees on the bottom so that the degrees would cancel. So the degrees cancel, and I end up getting 30 pi over 180, which is equal to, you can just divide 10 into both of them. That's 3 pi over 18, or pi over 6. So you'll want to pause the video and get that down. But 30 degrees is pi over 6 radians, and there's the conversion. So I'll get rid of that real quick, and I'll write that right here. So this is pi over 6 radians. Now, let's do 45 degrees up here. 45 degrees times. It is the same ratio. You want to get rid of the degrees. The ratio is always pi to 180 or 180 to pi. And we want the 180 degrees in the bottom so that these will cancel. And then we do a little bit of math here. This is 45 pi over 180. And if you divide 45 into both of these, this just becomes pi over 4. So 45 degrees is pi over 4 radians. Keep that in mind. We will be using radians for the rest of this class. This is going to be incredibly handy in helping you convert between them quickly. Instead of having to do this math every time, you just do it once and then look back at your circle in the future. So 45 degrees is pi over 4 radians. Let's try to keep that in mind. So this is pi over 4 radians. Now let's do 60 degrees. 60 degrees, which is right here, is where I'm getting this from, by the way. 60 degrees. We're going to multiply that by pi over 180 degrees. The degrees are on the bottom so that they cancel. If we put it on top, we would have like a degrees squared, which doesn't make any sense. This is 60 pi over 180. We don't write the degrees because they canceled. This is obviously 6 pi over 18. Or, if you divide 6 into both of these, this is just pi over 3. This is just pi over 3. So we'll just write pi over 3 here. Okay? And I'm going to have to write that again, but we'll just write pi over 3 right there. No big deal. And then we'll do the last one for 90 degrees. 90 degrees. We want to convert that to radians, so put the pi on the top, the 180 in the bottom. These will cancel. That's why we put the 180 on the bottom. Remember, you always multiply by a fraction that has 180 degrees and pi in it. One on the top, one on the bottom. Whatever you want to cancel out, that's what goes in the bottom. So in this case, we wanted to cancel the degrees, so that goes here. That's it. This is obviously 90 pi over 180, which is obviously 9 pi over 18. And obviously 9 is 1/2 of 18, so this is just pi over 2. So 90 degrees is pi over 2 radians. So for the rest of the class, I'm going to say pi over 2, and when you think pi over 2, that's a right angle, because pi over 2 is 90 degrees, and 90 degrees is a right angle. So that's how that works. So keep in mind, 90 degrees is pi over 2 radians. And let's just write that right here. Okay, now we can continue around the unit circle and see what the rest of these are. We could do 120 degrees, 135 degrees, 150 degrees, 180 degrees. That's a really easy one. And just keep going around and answer the rest of this. There is an entire bottom to this that we'll fill out in just a second, but I just want you all to keep in mind that there is a pattern to these numbers. So let's look back at this. So as we go back to this, I want to write, we'll do it in a nice blue here. I want to write these angles out. And I want to write these angles out pretty simply. So if you come along and look at the multiples of, we'll do the multiples of 45 degrees first. These are the easy ones to fill out. So multiples of 45 degrees. So 0 degrees is a multiple of 45, 45, 90, 135, 180. It continues around the rest of the circle. But basically we start at the positive x-axis, 0 degrees, and we count every other one. That's all the multiples of 45. I hope you would agree with that. If you don't, pause the video and try and convince yourself that that's 45 degrees, that's another 45 degrees, that's another 45, and that's another 45. You should be able to convince yourself of that fact, though. We're going to count like this, and I'm going to put this outside of the box kind of tinier, but we count like this. Here's the radian value. This is 0 pi over 4. 0 pi over 4 reduces to 0. This is 1 pi over 4. This is just 2 pi over 4. Okay? But now 2 over 4 reduces to 1 over 2. But we're going to skip over 120 and do 135. So by this logic, see, look, we're doing 0, 1, 2. So the next one should be 3 pi over 4. So we skip over 120 and we do 135. So this is 3 pi over 4. And this is how I remember it. And then we skip over the next one, and this is 4 pi over 4. And we keep that in mind. Now, 3 pi over 4 isn't going to reduce. 3 pi over 4 isn't going to reduce. So the actual value that we put in here is 3 pi over 4. We put the reduced fraction in the box. 4 pi over 4 definitely reduces. 4 over 4 is 1. This is just pi. So there's pi radians in half a circle. 180 degrees is pi radians. That's how you read that. And you can continue around the rest of the way, as we will in a second. So that's all that there is for that, and that's the first part that we do there. So let's look at the next part here, which I'll do in a nice, let's do that in a nice green. Why not? So now I want to look at the rest of these, the 30, the 60. You can include the axes on this one as well, 90, the 120, the 150, and the 180. These are all multiples of 30. You can include 0 in there as well. So you can look at this as, these are now, instead of multiples of pi over 4, these are multiples of pi over 6, which is what 30 degrees is. So this is also 0 pi over 6. This is 1 pi over 6. We then skip over the 45, because that's not a multiple of 30, but 60 degrees is a multiple of 30. So it'll be the next one. Instead of 1, it'll be 2 pi over 6. But 2 pi over 6 reduces to pi over 3, so we're good to go on that. 90 degrees is multiple of 30 as well. This is 3 pi over 6. Okay, but that reduces to pi over 2. We'll look at the next one. So that'll be 4 pi over 6. We'll then skip over 135, because that's not a multiple of 30, but 150 is a multiple of 30, so that must be 5 pi over 6. And then 180 is also a multiple, that's 6 pi over 6. And then we go back around and we write in the versions that reduce. So look here. We've got everything else. Look, 2 pi over 6 reduces to pi over 3. 2 over 6 is pi over 3. That's all there is to that. 4 pi over 6 reduces to 2 pi over 3. And 5 pi over 6 reduces to nothing. It stays 5 pi over 6. 6 pi over 6 reduces to pi again. 3 pi over 6 reduces to pi over 2 again. 0 pi over 6 reduces to 0 again. And you'll notice all of these patterns. Now, it's the numbers in orange here, the numbers in the boxes that we care about. We don't actually care about the rest of these numbers. But blue is counting by pi over 4s. You can see those. That's the ones that are multiples of 45 degrees. So 0, 45, 90, 135, 180, and so on. Those we can count by pi over 4s. So 0 pi over 4, 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4. And then for 30 degrees, since 30 degrees is just pi over 6, we can count by pi over 6s. So 0 pi over 6, 1 pi over 6, 2 pi over 6. 3 pi over 6, remember you also count 90 degrees because it is a multiple of 30. 4 pi over 6, 5 pi over 6, 6 pi over 6, and then just reduce whatever those fractions are and put them in the box. And that is the top part of the radian measures for the unit circle. And if you're worried about all this extra color stuff, remember the only thing that we have to write are the things that are in orange. So just the things in the box are the things that you need to memorize. But remember, 0, pi over 6, pi over 4, pi over 3, pi over 2, 2 pi over 3, 3 pi over 4, 5 pi over 6, pi. That's just, it seems random. It seems arbitrary. It seems like there's a bunch of just crazy numbers in here. What number goes where? Is it a 6? Is it a 3? Is it a 4? Don't try to memorize any of that. Just remember, you're counting around by multiples of pi over 6 and pi over 4. And those are the only two numbers you need to remember. So you can walk around, 45 degrees goes with pi over 4, 30 degrees goes with pi over 6, and just walk around and count that. So what I recommend that you do right now is you draw a unit circle, at least the top half of it, just like this, but blank, just like it was just a moment ago. So you can rewind to that part in the video, copy this yourself onto a piece of paper. I highly recommend this. And write these out yourself until you can do this without having to look back at the video. It might take half an hour for you to get this down. But the key in this is that you're walking up this by multiples of pi over 6 and multiples of pi over 4. I highly recommend that you do this. There will be a point in my class on a test in person in which I will hand you, for at least half of the test, so 5 points on your final grade, a blank unit circle, and you will have to fill it out on your own with no aid. That will happen before the end of this semester. I assure you, it will be part of some test somewhere, usually the first one, and I want you to look at this and try and figure out how to memorize it. And I just gave you the way to do it. You don't have to write any of these numbers that I didn't write in the box. It's not necessary at all. However, I just gave you the way to look at this. So if you need that again, hey, rewind it. Watch it a couple more times. See if you can follow along with me if you haven't already done that. You should be taking notes as we go about this. See if you can't do the top half of this just for the angles. So go ahead and pause and give that a shot. The next thing I want to talk about are the coordinates. So out here on the unit circle, remember this is the unit circle has radius 1, so we can label these points. So literally these points out here, this point and this point and this point, and so on and so forth. We can label all of those. I'll leave them white though because they look better that way. So this first one is pretty obvious. This is the point where we come out this distance. Well, what is this distance along this straight line here? Well, it's 1 because it's the radius, and we didn't go up at all. So that's the point 1, 0. That's pretty obvious. This up here at 90 degrees is the point 0, 1 because we didn't go out at all and we came up a distance of 1 because, again, this distance from the center to the outside is called the radius, and that's just 1. And then over here, it should be pretty obvious that this is negative 1, 0 as well. And again, I'm talking about this point on the unit circle. This is your x-axis going across through here. This is your y-axis coming down through here. We're on a coordinate plane. So that's those points. The question is, what are the rest of these points? And how do you get them? And where do they come from? And the answer is surprisingly deep. It comes from just right triangle trigonometry that you've seen before. All right, so let's talk about how to get the coordinates for each one of these. So you'll see that I went ahead and filled out that each one of these are over 2, and that's an easy pattern to remember as you're going through here. And then be very careful with this when you put this sort of thing up. So in order to figure out this pattern, it's pretty easy. You simply say that the cosine begins up here at the square root of 1 over 2. So cosine is x, remember. Now the square root of 1, but I'm not going to write that. I'm just going to write 1 because that's what the square root of 1 is. And then it's the square root of 2 and the square root of 3, like this. And then we do the exact same thing back the other way. So it's the square root of 1, which is just 1, the square root of 2, and the square root of 3. And we'll go over in 5.4 where these numbers come from. It's just right triangle trigonometry, and there's some pretty cool visual examples of why. But right now, if I try to come in here and draw the triangles where I drop this down and make this a right angle and do the reflection and everything to figure out why that is, it's just way too busy on the unit circle right now. There's too much stuff going on, so we're not going to worry about that too much. Now you'll notice that I also have this side over here filled out as well, over here in quadrant 2. And these 3 points here, you'll see that I already have them filled out, except they have negatives in front of the x parts. And that's because in quadrant 2, which is why we wrote this stuff over here, it's negative positive. So remember, in your quadrants 1, 2, 3, and 4, quadrant 1 is both positive, quadrant 2 is x is positive, x is negative, y is positive. In quadrant 3, they're both negative, and in quadrant 4, x is positive and y is negative. So you'll see that I've went ahead and filled this out, and it's always over 2, and we'll see why that is again in 5.4. But for now, I just want you to look at this red line here. In order to get the coordinates here, if you have this first quadrant memorized, which you should absolutely do, then the rest of them fall in naturally, and I'll show you how. So you just bring this over, okay, and take and copy the exact same numbers straight over. So it's 1/2 and root 3 over 2. So we're going to write that. We're going to write 1/2 and root 3 over 2. Okay, and then over here, you bring these numbers over as well, both square roots of 2. Except the first one is negative, just like up here. The first one's negative here, the first one's negative here. So we're going to bring that straight over. So it's a couple of root 2's. And the ones in the middle here, if you will, the ones in the middle here are always going to be your square roots of 2. The ones that are multiples of 45 degrees. are going to be your square roots of 2 that are on the middle of the angles here. Okay, and then if you bring this one over here, you'll do the exact same thing, and you get square root of 3 and 1 again. And that is the angles for the top half of this. So now we're going to go ahead and fill in the bottom of this unit circle, and we'll be good to go. So we're going to do the same thing again with the angles. We're going to do the same thing again with figuring out how to get the coordinate pairs in there. So now we've zoomed out, and this is the entire unit circle, and you can see that we're missing some other values. So we're going to go ahead and fill in the rest of the radians going around, and then we'll see what the rest of the coordinates are as well, as best we can. And I may have to put some of the coordinates inside so that we can see it, but I'll show you how to do this. So let's just continue our pattern. Let's continue with our pi over 4s. So let's count over by pi over 4 again. So remember, this is 0 pi over 4, 1 pi over 4. We're counting every other one. So 2, 3, 4. So that must make this 5 pi over 4. So 5 pi over 4. Then we skip 1 and we do 6 pi over 4. And then we skip 1 and then we do 7 pi over 4. Then we skip 1 and we do 8 pi over 4. So we'll do 8 pi over 4 here. So 8 pi over 4 is the same thing as 0 pi over 4. It's this same guy. Except the only difference is 8 pi over 4 is we've went around one revolution. 0 pi over 4 is we never win at all. So it should be pretty obvious at this point that we can fill in these. 5 pi over 4 doesn't reduce, so it just goes in the box. 6 pi over 4 does reduce. You can put 3 into both of those and get, or you can put 2 into both of those rather and get 3 pi over 2. 7 pi over 4 doesn't reduce. And then 8 pi over 4 does reduce. It's 2 pi. And we'll put 2 pi here. That's why we left the extra space. And that's as far as we go. We just go around one revolution. And we can also say that 0 degrees is the same thing as 360 degrees. It's the same thing. So we can put both of those on there. And all that we have left to do is just fill out in green here the rest of the pi over 6s. So 6 pi over 6. So 210 is a multiple of 30. So this is 7 pi over 6. I'll write it right here. This is 7 pi over 6. Then we skip 1. 8 pi over 6. And remember, when you're counting by pi over 6s, you also count these guys here. So this is 9 pi over 6. This will be 10 pi over 6. This will be 10 pi over 6. This will be 11 pi over 6. And then this will also be 12 pi over 6. Okay? And then let's go in and fill those in. So we're just counting every multiple of 30. So 210, 240. This is 270 degrees, since we need it. 270, 300, 330, and 360. Those are all multiples of 30. And if you look at and know your degree measurements, which you should, basically everything that ends in a 5 is going to be a multiple of pi over 4, and everything that ends in a 0 is going to be a multiple of pi over 6. So you're going to count pi over 6 if it ends in a 0. So everything that ends in a 0 is what you'll count for pi over 6. So we'll go ahead and use these green guys. 7 pi over 6 doesn't reduce, so we'll go ahead and put him in the box. 8 pi over 6 does reduce. You can put a 2 in each one of those. That'll give you 4 pi over 3. 9 pi over 6 reduces to 3 pi over 2. 10 pi over 6 reduces. That's 5 pi over 3. 11 pi over 6 doesn't reduce. 11 pi over 6 doesn't reduce. I always do that. 11 pi over 6 doesn't reduce. And it goes right in the box like that then. And now we've filled out all the boxes. So we've done all the radian measures, and that's all the radian measures. And you can try to remember these. 0, pi over 6, pi over 4, pi over 3, pi over 2. Those are worth keeping in your mind, but 2 pi over 3, 3 pi over 4, 5 pi over 6, pi, all of these. I mean, I've got them memorized because I've done this for a long time, and you'll have them memorized by the end of the class, but at first, don't concern yourself with remembering that pattern. Just remind yourself of the pattern of pi over 4s and pi over 6s. You count by pi over 4s, starting with the x-axis, every other one, or any of these where the degrees ended in 5, or are on the x or y axis. And then the zeros you can all count by pi over 6s. And if you just remember that thing, you don't even have to remember to get the 90, 180, 270, and 360 on the pi over 4 pass. You can do it on the pi over 6 pass and it'll come around eventually. It's whatever you want to do. But you're literally just counting 0, 1, 2, 3, 4, 5, 6, 7 pi over 4, 8 pi over 4 all the way around. And then you're counting 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 times pi over 6 all the way around, and that'll get everything. Just reduce the fractions and put them in the box. Reduce the fractions. Do not leave the fractions unreduced, please. Now for the bottom half of the unit circle's coordinates, it's just as easy as the top half, except there's just a little slight change that's not that difficult. So you have the exact same pattern that everything is over 2, so I'm going to go ahead and put in all those over 2's as well. And that isn't going to change at all. So over 2, comma, over 2, and over 2, and then we've got an over 2, and over 2, and then finally something over 2, something over 2. They're all like that. And then go grab your coordinates. So in coordinate 3, both of them are negative. So all three of these will be negative. So this will be negative, this guy will be negative, this guy will be negative, this guy will be negative, which I'll put this negative up here so it's a little bit easier to see. This guy will be negative, and this guy will be negative. And then in quadrant 4, the first one's positive and the second one's negative. So first one's positive, and then the second one is negative. So the second one is negative, the second one is negative, the second one is negative. And just keep that in mind. And that pattern is the same as always. And the unit circle is just about patterns. And then we just pull down, like this, the root 3 and the 1. So pull down the root 3 and the 1, except they're both negative this time. The root 3 and the 1. Then we're going to pull down the double root 2's, just straight down, like that. So we'll just pull down the double root 2, so the square root of 2 and the square root of 2, except they're both negative. Remember, they're both negative. And then we'll do the exact same thing here. We'll pull down the 1/2 and the root 3 over 2. 1/2 and the root 3 over 2. So the 1 goes here, and the root 3 goes here, because we're just copying it. Let me try that again. There we go. And then your choice on this fourth one. You can either pull this number straight down, which is 1/2 and root 3, or you can pull this one straight over, which is 1/2 and root 3. It's up to you which way you do it. I'm going to pull across, but 1 and root 3 are the things that go on top. So 1 and root 3. And remember, the first one is positive and the second one is negative because you're here in quadrant 4. So I'm going to pull across the double root 2's because we're in the middle. It's pretty easy to remember. And then for this one, I'm going to pull over the root 3 and the 1. So we're going to go ahead and write all that out. So it's double root 2, and then it is the, we're pulling across the root 3 and the 1. Either pull it down or pull it from the left, either way. But those are all of your coordinates. Now, you folks should probably write the coordinate on the outside here for both of these guys. I don't have the room. If I zoom out any further, this becomes very difficult to read, but you should probably write it on the outside of your unit circle when you get a copy. But those are the coordinates in the bottom half. And I want to show you a very crucial pattern here that you may notice. And you may have already noticed, but if you look at these guys here, you'll notice that they're, in absolute value, they're the same distances. Root 3 over 2 and 1/2. And it's the same over here. And it's the same down to here. And it's the same here as well. And you'll notice that everything on this box, everything on this rectangle, has the same numbers. And the only thing that changes is the stuff that we went over up here. So I want to do a green box for the root 2 over 2's, and look, they're all root 2 over 2's, every single one of them. They're all root 2 over 2. This is root 2 over 2, root 2 over 2, root 2 over 2, and root 2 over 2. They're all the same. Look at that. All of those on the corner of that box. It's the same number, and the only thing that changes are these signs up here. That's really cool. And then I'll do the last one here in hot pink, but you'll notice that they're all 1/2 root 3 over 2, and the only thing that changes is the sign. And because of this box, if you know any corner of this box and you know what your signs are, these things, in every single quadrant, you're good to go. Which is why I say memorize the first quadrant, and the rest of this comes together very nicely. And take a moment and step back and look at all the ridiculousness that this is. And you can see that there are so many patterns inside of the unit circle. It's why I love this thing so much. But really, all you have to remember is how to count by pi over 6 and pi over 4, all the way around the circle, or how to count by 30s and 45s to get your degrees. And then the 1, 2, 3, 3, 2, 1, 1, 2, 3, 1, 2, 3 pattern as you go around that way, with the square roots, square root of 1, square root of 2, square root of 3, that everything's over 2. And then this little box pattern, and then you've remembered everything. And as long as you don't forget to label these points, which are incredibly easy to remember, because they're literally just on a unit circle 1 unit away in whatever direction, you've labeled everything. And all of this information is available and hugely helpful in trig, as we'll see in just a moment. But it's all from just a few very simple patterns. And this looks like a lot of information, but remember, we built up layer by layer by layer. This thing tells us every single major degree in angle, in degrees, in radians, and it tells us its sine and cosine value, which we'll get to in just a moment, in fully reduced form, with all the extra information that comes along with this graphical, intuitive look. So this thing is incredibly useful, and the way that it's put together is also important. Now, when you finally draw the final version of the unit circle, if I were to ever ask you to do this on a test, which I will, the things that you need to put on there are all in orange. Everything's in orange. Only the things in orange actually need to be on the unit circle, and the degrees. The degrees also need to be on the unit circle. Otherwise, none of the rest of this needs to be on there. Everything else is just what we use. So none of the lines for those boxes that we just had, none of the green stuff, none of the blue stuff, just the stuff in orange, just the stuff in the boxes and the coordinates. And if you want to just try to verbatim memorize this thing without memorizing the pattern, I wish you good luck. But the whole point of this video is to give you a very quick and easy way to learn the unit circle in a way that will be useful to you. And speaking of being useful, let's go ahead and look at some examples where we use this thing. If T is some angle in R, and XY is a point on the unit circle corresponding to an angle of theta, then we have that X is cosine theta, Y is sine theta. X is cosine, Y is sine. X is cosine, Y is sine. X is cosine, Y is sine. Get that in your head, please. And the way that I remember it is, look at the first letters. C comes before S. X comes before Y. That is legitimately how I remembered that before I just said it a billion times. So remember that. X goes with cosine, Y goes with sine. X goes with cosine, Y goes with sine. Please put that in your head. So let's look at these. Here's what we can do with these. Using the unit circle, we can answer these questions. Find the exact value of sine of pi over 3, sine of 3 pi over 2, and sine of negative pi over 6. So I'm going to show you how to read your unit circle. Remember, sine is y, sine is y, sine is y. You don't have to write this, but just remember sine is y. So the sine of pi over 3 is as simple as, look at your unit circle right now. Find pi over 3 as a radian measure. You input radians or degrees to the sine function. Find pi over 3. That's 60 degrees. Find that. Since sine is y, look at the y coordinate. What is the y coordinate when your radian is pi over 3? It's 1/2. So we say that the sine of pi over 3 equals 1/2. That's it. It's that simple. The sine of pi over 3 is 1/2. The sine function gives you the value on the unit circle at that radian measure. That's all that it does. So the sine of pi over 3 is 1/2. Let's look at the sine of 3 pi over 2. you try this one. Pause the video, see if you can't figure out what the sine of 3 pi over 2 is. Again, you're just going to go look at 3 pi over 2 on the unit circle. That's 270 degrees. That's the negative y-axis. And you're going to say, well, sine is y. Remember, sine is y. So what is the y-coordinate there? It's negative 1. So the sine of 3 pi over 2 is negative 1. That's it. The last one's a little bit harder. The sine of negative pi over 6. So if you look around that, you'll notice that all of those numbers are getting bigger. That is, as you go around counterclockwise, the numbers get bigger. So if you wanted to go around negative pi over 6, instead of going up in quadrant 1, just look at your unit circle. Instead of going up in quadrant 1, pi over 6, or 30 degrees, you'd go down into quadrant 4, 30 degrees, to get your negative pi over 6 angle. So negative pi over 6 and 11 pi over 6 are coterminal angles. They're the same thing. Again, convince yourself of that. Look at your unit circle. If you just rotate clockwise, pi over 6, you're on that part. And when you look at that, you'll notice that the sine there is nothing but negative 1/2. And again, the reason that is, and I'll draw a rough circle here for you and show you, is instead of coming up like this to do positive pi over 6, negative pi over 6 is just coming down like that. So we're reading this point here. And since it's sine, we're reading this part here, the negative 1/2 part, not the root 3 over 2 part. Okay? Now cosine is x, but it's the exact same thing. So go ahead, pause the video. I'll bet you can do all three of them. It's the exact same process, except it's just the x coordinate instead, because cosine is x. So go ahead, pause the video. I'll bet you, without even going over this, you can do all three of them. You might have to think about what negative pi over 2 looks like, but it's the same logic that I just showed you for this last part here. So go ahead, try them. See if you can't write them down. If you can, you know it. If you can't, that's okay. Come back, watch it, you'll learn. Let's talk about the cosine of pi over 6. The cosine of pi over 6, look at your unit circle. Cosine is x, cosine is x. So look at the x-coordinate on pi over 6. The x-coordinate on pi over 6 is root 3 over 2. Okay? Let's look at 2 pi over 3, or 4 pi over 6, if you will. What's that going to be? So the cosine of 2 pi over 3, just look at your unit circle, guys. The cosine of 2 pi over 3 is just negative 1/2. Just looking at your unit circle. The cosine of 2 pi over 3 is just negative 1/2. And then the cosine of negative pi over 2, well, instead of going up to 90 degrees, you go down to negative 90 degrees. That's the same thing as 270 degrees, or 3 pi over 2. And the cosine there is 0. And that's it. You'll notice how these two examples, which are the only two examples I'm doing like this, are almost impossible to follow along if you didn't actually write down the unit circle. So if you didn't do that, and this isn't making any sense, it seems like I'm just pulling these numbers out of thin air, that's because you didn't have a unit circle in front of you. So do that. Back up, get a unit circle in front of you, and come back and rewatch this, and you'll understand what's going on. So here's the last thing. It's the single most important thing in all of this class in terms of identities is the Pythagorean identity. This thing is going to be the crux of so many problems in both this class and when we get to calculus, and especially when we get into Cal 2. This becomes incredibly useful. So I want to tell you this. The Pythagorean identity states that for any real number theta, cosine squared theta plus sine squared theta equals 1. And I want to talk about what this means. So another way to write this would be cosine of theta all squared plus the sine of theta all squared equals 1 squared, if you will. You don't have to square that, though. So this is just shorthand. Cosine squared theta and cosine theta squared, this is shorthand. We prefer to write it like this because there's some ambiguity. If you write cosine theta squared, the question is, do you mean the cosine of theta squared? Or do you mean take the cosine of theta, then square that? Which one do you mean? There's ambiguity there. We don't know which one you mean. You have to clearly either put the parentheses here or put the parentheses here, and it matters, and we don't like ambiguity in mathematics. So instead, we just move the 2 over here. That's it. That's all that means. And that's what we prefer to write. So cosine squared theta, sine squared theta equals 1. Where does that come from? Well, it should be pretty obvious, but if it isn't pretty obvious, let me show you. What is cosine theta? Cosine theta is just x squared. I'm just replaced cosine theta with x plus sine theta is just y squared equals, and then 1 was just the radius of a right triangle that you can make. So this is just r squared, but this is just 1 squared, and it's pretty obvious now why this is called the Pythagorean identity. This is just the Pythagorean theorem applied to your unit circle. If you have a circle, at any point on that circle, you just have a right triangle, this little guy here. And if that's your x, and if that's your y, and if that's 1, and that's a right triangle, it should be pretty obvious that the relationship is x squared plus y squared equals 1 squared. Because it's a unit circle, we know that the hypotenuse is 1, the hypotenuse being the radius. So then, if x is cosine theta and y is sine theta, like we said up above, well then cosine squared theta plus sine squared theta equals 1. That's always true. And that's nice. And that means that if you take any of those coordinate pairs, and you can try it, take any coordinate pair, root 2 over 2, comma, root 2 over 2, root 3 over 2, comma, 1/2, 0, comma, -1, any of them, and you plug them into this. So 0 squared plus -1 squared, that'll equal 1. Square root of 2 over 2 all squared plus square root of 2 over 2 all squared, that'll equal 1 too. Any of those, if you plug them into this formula, you will get 1 out. And indeed, it doesn't just work for the main ones that we marked. It works for any points on that entire circle. In fact, you could define the unit circle by this equation. This is the equation for the unit circle. And those of you that remember, x squared plus y squared equals 1 is the equation in rectangular coordinates for the unit circle as well. This cosine squared theta plus sine squared theta equals 1 is in what we call polar coordinates with r set to 1, and that's something that we'll get to way later if we have time for some extra stuff. But I want to now derive the other 2 forms of the Pythagorean identity, and these are just the basic forms of the Pythagorean identity. We'll get a couple more later. But all that we're going to do is we're going to rewrite this a couple times. So cosine squared theta plus sine squared theta equals 1. And sometimes we write it the other way, sine squared plus cosine squared. Sine squared theta plus cosine squared theta equals 1. And then we're going to write it over here again. Cosine squared theta plus sine squared theta equals 1. And I want to go ahead and state that it is incredibly imperative that you always write the thetas. If you don't, whatever it is you're doing is just wrong. Please write the thetas. If you just write cosine squared, that makes about as much sense as saying the square root of... That's it. Or just squared. When what you meant was x squared, you just write the little 2 floating there. Or you write just the natural logarithm, right? Or you just write e to the, nothing like that. I mean, this just means e to the first. But the natural logarithm, the square root of nothing, cosine squared of nothing, the sine of nothing, that doesn't mean anything. You have to put an argument into it. So please, don't write cosine squared plus sine squared equals 1 to tell me that that's the Pythagorean identity. Like, that's what you mean. But these both need to have the same argument. They could both be t's. They could both be x's. They could both be y's. or in our cases, they can both be thetas, and that's always going to work out nicely for you, okay? So all we're going to do on this is just subtract cosine squared to the other side. And you should see pretty clearly that this just gives you that sine squared theta equals 1 minus cosine squared theta. So that's another form. Keep that in mind. And then the other way is we're going to subtract sine squared to the other side. And we're going to get the cosine squared theta equals 1 minus sine squared theta. And that's the other form. And those are the three basic forms of these. And this will come in incredibly handy later down the line when we're doing proofs, which totally show up in this class, which you should totally expect. So those are the three forms of the Pythagorean identity. And you'll definitely want to write those down somewhere where you have access to them. And you'll want to put this top one in your head. You'll need to have that in your head. So jam that in your head. There's not a lot of memorization in this class after this point. But this section, you should definitely put everything in this section in your head. If you're ever going to study anything to the point to where you can basically write down these notes on your own, write down all of this. The only thing that you do not need to shove in your head is the definition of the unit circle. That's what the rest of trig is about, is explaining what exactly that means. But these other three things, how to draw the unit circle itself, that x equals cosine and y equals sine, and the Pythagorean identity and its other two forms, all of that should be in your head from now going forward. So take some time, get that in there, do some practice, and see what you can learn.